Hey everyone, in this lecture video I'm going to talk about a couple of different radical reactions. The first will be radical addition to pi bonds, and the other will be allylic bromination. Allylic bromination is when a, a hydrogen at the what's called allylic position is substituted with a bromine atom, where the allylic position is that position right next to a carbon-carbon double bond. And then at the end, we'll talk a little bit about the use of these reactions in synthesis and do a little bit of retrosynthetic work together. Hydrogen radicals, first again, though, we're going to talk about radical addition to pi bonds. And we're going to look at the idea of radical addition of HBr across pi bonds. Now, radicals can react with pi bonds because the carbon-carbon pi bond, just the pi bond, is relatively weak. It's estimated that that bond is in the 250 to 260 range, and that energy is much lower than your prototypical carbon-hydrogen bond. Those, at the lowest are, 350 at the lowest, and usually much higher. And you've actually been looking at these kinds of reactions earlier when you were looking at radical reactions with simple alkanes. So here now, when we look at radical additions to alkenes, we're breaking bonds that are even lower in energy than carbon-hydrogen bonds. Now, you've already seen addition of HBr across an alkene when you looked at electrophilic addition. And in those reactions, the first step was, in essence, a protonation of the alkene with H+. H+, of course, from hydronium, H3O+. And so you could protonate your alkene at two different locations. At least for this example, these two carbon atoms are different. This is an asymmetric alkene, of course. You can have hydrogen protonate this alkene and be attached, proton, protonate this alkene such that the hydrogen atom is bound to this carbon, and the corresponding carbocation intermediate is located here and forms a secondary carbocation. Alternatively, of course, you can have H+ add across this pi bond such that the H is attached to this carbon and have a primary carbocation intermediate. Of course, secondary carbocations are much more stable than primary carbocation intermediates, and so the products that go through this more stable carbocation intermediate are favored. And that turns out, in this particular case, to be this product where the bromine adds at this secondary position, notably favored over this primary product. And we call this the Markovnikov product, or Markovnikov addition is the term that we use. Now, interestingly enough, in free radical halogenation of the pi bond, we see precisely the opposite selectivity that's observed in electrophilic addition. Instead, the so-called anti-Markovnikov product is favored. And how do we explain that? As with virtually all explanations in organic chemistry, it's to look at the reaction mechanism and see how one reaction pathway is favored over another. So let's take a look at this reaction mechanism, and we're going to use that to help us determine why this anti-Markovnikov product is favored. First, we're going to start with this free radical initiator. This oxygen-oxygen bond right here is very weak and splits either with heating or with relatively low wavelength light. So here I just have a generic scheme where I have the oxygen-oxygen bond splitting homolytically to yield two of these radicals. This radical then reacts with HBr, abstracting hydrogen, to yield bromine radical. Okay, now this bromine radical now is free to react with the pi bond, and it can react and form a bond to two different carbon atoms because my alkene here is asymmetric. In this particular scheme, the bromine is forming a bond to this carbon atom. The way this arrow is arced like this tells you that this bromine is forming a bond to this carbon atom, the arc towards the atom that's forming the new bond. The radical intermediate then is this secondary radical intermediate. Okay? Alternatively, the bromine radical could add so it is bound to this central carbon atom. In doing so, this would be the primary radical intermediate that would result. Now, radicals tend to exhibit properties that are similar to those of carbocations, including because they act electron deficient, just like a carbocation, not just like a carbocation, but carbocations also act electron deficient. And so a tertiary carbon radical is more stable than is a secondary carbon radical than is a primary carbon radical. And then here, just as a quick aside, radicals that can resonance delocalize are even more stable than these tertiary, secondary, or primary radicals that are where the radical electron, that lone unpaired electron, is localized. And so here in this particular example, clearly this is the more stable intermediate. So this is the reaction pathway that's favored. And then here at the end, the more favored radical abstracts hydrogen from HBr, yielding the anti-Markovnikov product and generating more Br radical. As a quick aside here, the only species that undergoes this selective anti-Markovnikov radical addition to alkenes is HBr. For its enthalpic and entropic reasons, HI does not undergo radical addition to alkenes. And then for HCl, as I recall, it's enthalpic reasons that HCl does not undergo radical addition to alkenes. And then here are just a couple of examples of reactions that we might look at in class together on the board. All right, next we will look at allylic bromination, as promised before. Allylic bromination is accomplished using a really cool reagent, NBS, or N-bromosuccinimide is the species I'll focus on. It also has the chlorine analog. The chlorine analog also exists, N-chlorosuccinimide. N-bromosuccinimide is really cool. Not only is this compound a source of bromine radical, but it's also a source of electrophilic bromine, which you'll actually get to see here momentarily. This reagent is used quite a bit in organic synthesis. I've used this multiple times for different transformations. Incredibly useful reagent. Let's talk about its use in this process, allylic bromination. Here at the top, let me kind of hide the mechanism. Right here is a classical allylic bromination using NBS to yield bromine substitution at this position, the allylic position adjacent to the alkene. To understand why this reaction proceeds with addition at the allylic position rather than addition across the pi bond, let's look at the mechanism. First is homolytic cleavage of the nitrogen-bromine bond. This bond's pretty labile to yield a pair of radicals. The Br radical can then go and abstract hydrogen from this allylic position. This is the weakest carbon-hydrogen bond on this molecule because the product is resonance stabilized. And then HBr forms as a result of this hydrogen abstraction. The HBr, the concentration of HBr in these reactions is kept quite low because HBr reacts rapidly with N-bromosuccinimide to generate succinimide and molecular bromine. And this molecular bromine is highly susceptible to reaction with carbon radicals to yield carbon-bromine bonds, shown down here, where my resonance stabilized carbocation radical reacts with molecular bromine to yield my brominated product. Here in this particular instance, this is a stereogenic center, so you get a mixture of what would be the R and S stereoisomers. Oh, here just real quick, this is just the mechanism for the reaction of N-bromosuccinimide with HBr. As I said earlier, NBS is a source, a source of electrophilic bromine that can be attacked. And so here is the attack of bromide pulling electrophilic bromine off of N-bromosuccinimide. It happens to be protonated N-bromosuccinimide, but that just makes this bromine all the more available for removal by a nucleophile. Oh, and then here are a set of reactions that I strongly encourage you to take a look at on your own time before class. Maybe write down what you think the products might be, and we'll discuss a couple, if not all of these during lecture. Real quickly, I thought it worth our time to discuss why it is that NBS reacts at the allylic position rather than across the alkene. Okay? And I guess in a nutshell, it has to do with the concentration of HBr in solution. When the concentration of HBr is high, under conditions that favor formation of radicals, reaction across the pi bond is favored, and that's shown here on the right-hand side. So whenever there's bromine radical and there's a relatively high concentration of HBr, you end up having addition across the pi bond to form the brominated product. When the concentration of HBr is low, though, you tend to get this reaction pathway as favored. You can also read about this in the module for class. Oh, and then lastly, this idea of radical halogenation in synthesis. And so what we'll do is focus a little bit on addition to alkenes, right? Addition of HBr to alkenes, and then allylic and benzylic bromination. And actually, I think what I'm going to do is just propose a scheme to you guys. Yeah, let's do that. Yeah, right here. Here, I came up with some questions for you guys. Here, this is the idea of this arrow is what's called a retrosynthetic arrow. It means, for all intents and purposes, the arrow means this thing from this thing. Okay? So here, for example, the question is, hey, this is your synthetic target. One wants to make this molecule. How would you make this molecule from this molecule? Okay. And so here I've just given you just one quick little hint, and that is that you can make this target molecule from this species in 3 steps. And what I'll do is, rather than explain it here in the video, I think we'll just do it in class, where we'll sit down and we'll think logically about how it is one can convert this species into this molecule right here. Interestingly enough, the method that we'll use is we'll actually start here and we'll say, all right, how do I make this molecule? What is the precursor to this molecule that I know I can convert into this? Okay, so we'll basically go one step down. We'll say, oh, this molecule comes from B. And then I'll say, oh, I know that I can make molecule B from molecule C. And then I can say, oh, I know how to make compound C from this starting material. That's the approach that we'll take. Maybe we'll give this one a shot. This involves SN2 chemistry. I'm not sure how familiar we all are with that. So, this is one that we'll kind of put on the maybe list. And these ones I don't think we'll do for class unless we really feel like it. All right, that's the end of the pre-lecture video. Really look forward to chatting with you guys about these 2 different radical reactions that we talked about. And then also doing these retrosynthetic questions. These are super fun. It's a puzzle, and it's really enjoyable. It really stretches your mind. Have a great afternoon, you guys.